On July 23, 2012, a NASA satellite called Stereo-A was floating in space, minding its own business, when something slammed into it. It wasn't a rock, it wasn't debris, it was a cloud. 1 billion tons of magnetized plasma blasted off the surface of the sun, traveling at over 6 million miles an hour. One of the most powerful solar storms ever recorded. And it crossed Earth's orbit. Not near Earth's orbit. Through it, through the exact lane our planet drives around the sun. But here's the thing, Earth wasn't there. We had passed through that exact spot 9 days earlier. 9 days. That's the margin. That's how close the modern world came to an event that scientists estimate would have caused up to $2.6 trillion in damage and knocked out power for months. Not hours, months. And almost nobody heard about it. So today we're going to run the tape. What actually happens if a storm like that hits us head on? Because it turns out the answer isn't the lights go out. The answer is much, much worse than that. First, let's kill the myth. When you hear blackout, you picture a specific thing. The power flickers, your phone still has charge. You dig out some candles, maybe complain on the internet using your data plan. And by tomorrow, the day after, worst case, some crew in a bucket truck fixes a line and life snaps back to normal. That's the mental model. Blackouts are an inconvenience. And for almost every blackout you will ever experience, that model is correct. A tree falls on a line. A substation trips. Crews replace the broken part because the broken part is sitting in a warehouse somewhere. But a solar storm doesn't break the parts in the warehouse. A solar storm goes after one specific piece of equipment. A piece of equipment most people have never thought about for a single second of their lives. It weighs up to 400 tons. It costs millions of dollars. And here's the detail that should genuinely scare you. If it dies, you can't buy a new one, not quickly. In many cases, not for over a year. We'll get there. But first you need to understand what the sun actually did in 1859, because it's already shown us exactly what it's capable of. September 1st, 1859, a British astronomer named Richard Carrington is doing something deeply boring. He's in his private observatory, sketching sunspots by hand. Because that's what passed for entertainment in 1859. And then, right in front of him, 2 blobs of blinding white light erupt on the surface of the sun. He's just become the first human being to witness a solar flare. He has no idea what he's looking at. Nobody does. 17 hours later, the Earth found out. The sky caught fire. Auroras, the northern lights, which normally stay politely near the poles, exploded across the entire planet. They were seen in Cuba, in Hawaii, in Colombia, practically on the equator. In the Rocky Mountains, the glow was so bright that gold miners woke up and started cooking breakfast because they thought it was morning. Beautiful, right? Here's where it stops being beautiful. In 1859, humanity had exactly one piece of electrical infrastructure, the telegraph. Wires strung across continents, primitive, simple, barely even a technology. The storm attacked it anyway. Telegraph operators were thrown back from their machines by electric shocks. Sparks leapt from the equipment. In some offices, the paper, the actual telegraph paper, caught fire at the desk. And in the strangest detail of the whole event, some operators discovered they could disconnect their batteries entirely and keep sending messages. The storm itself was pushing enough electricity through the wires to run the network. Think about what that means. The sun reached across 93 million miles of empty space and powered our machines against our will. That event is now called the Carrington Event. It's the benchmark, the worst solar storm in recorded history. And it hit a civilization whose entire electrical grid was some wire and beeping. So the obvious question, the question this whole episode hangs on, is what happens when a Carrington event hits a civilization that runs everything on electricity? Quick detour, 60 seconds, because you need to know what the weapon actually is. The sun is not a calm ball of light. It's a churning ocean of plasma wrapped in magnetic field lines, and those field lines tangle, they twist, they store energy like a rubber band being wound tighter and tighter, and sometimes they snap. When they snap, the sun can hurl a piece of itself into space, a coronal mass ejection, a CME, billions of tons of charged particles wrapped in the sun's own magnetic field, fired like a cannonball. Most CMEs miss us. Space is big, Earth is a dartboard the size of a pinhead, but when one connects, it slams into Earth's magnetic field, the invisible shield around our planet, and starts shaking it. Therefore, here's the crucial part. A shaking magnetic field does something very specific. It's the same principle as every generator ever built. Move a magnetic field near a conductor, and you create electric current in that conductor. Now look around. What has modern civilization built? Thousands and thousands of miles of the longest conductors in human history. Power lines, pipelines, rail. We have, without ever intending to, wired the entire planet into one giant antenna. An antenna perfectly tuned to receive a solar storm. In 1859, that antenna was a telegraph network. Today, it's everything. If this all sounds theoretical, like something that only happens in the 1800s, I need to tell you about March 13th, 1989. That night, a solar storm hit Earth, not a Carrington-class monster. A storm maybe a third that size, a medium one. In the Canadian province of Quebec, currents from the storm began leaking into the power grid. Protective systems started tripping one after another, faster than any human could respond. The entire Quebec power grid, one of the largest in North America, collapsed in 92 seconds, a minute and a half. 6 million people in Canadian winter in the dark, no warning. Engineers watching their control boards light up with failures couldn't stop it because the collapse was moving faster than they could think. Quebec got its power back in about 9 hours, so inconvenient, scary, but survivable, right? Except for one detail, 1,000 kilometers away that almost everyone missed. That same storm reached down into a nuclear power plant in New Jersey, the Salem plant, and cooked one of its main transformers, melted its internals, destroyed it. That transformer was one of the giants I mentioned earlier, and the only reason Salem recovered quickly is that by pure luck, a spare happened to be available nearby. So a moderate storm in 1989 killed one of these machines from the other side of the continent, which finally brings us to the machine itself, the single point of failure for the modern world. Somewhere within a few dozen miles of you right now, sitting behind a chain-link fence in a substation you've driven past 100 times without looking, is a large power transformer. It's a beige or gray box, roughly the size of a small house. It hums, and its job is simple. It converts electricity between the ultra-high voltages used to move power across the country and the lower voltages that can actually enter a city. Every watt of electricity in your life passes through machines like this. No transformers, no grid, full stop. Now, 3 facts about these machines. Each one is worse than the last. Fact 1. When a solar storm pushes current into power lines, that current is the wrong kind. A slow, direct current the transformer was never designed to handle. It saturates the transformer's core and the machine starts overheating from the inside. The copper cooks, the insulation burns. There is no repairing it afterward. It's dead. Fact 2. These machines are not mass-produced. Each large power transformer is essentially custom-built by hand for its exact location on the grid. They cost millions of dollars each. They weigh hundreds of tons, so heavy that moving one requires special rail cars, of which only a handful exist. And the waiting list to have a new one built is measured in years, often from factories overseas. Fact 3, and this is the one that keeps grid engineers awake, utilities keep almost no spares. Why would they? Under normal conditions, these machines quietly run for 40 years. Nobody stockpiles a 400-ton multi-million-dollar object that statistically never fails. But a Carrington-class storm doesn't kill one transformer. Studies modeling a direct hit on the United States estimate a severe storm could damage or destroy hundreds of them, simultaneously, across the country, all needing replacements from a global supply chain that produces only a trickle per year, a supply chain that, by the way, also runs on electricity. Therefore, this is why the power comes back tomorrow dies as an idea. There is no tomorrow fix for this. The National Academy of Sciences and Lloyd's of London have both put recovery time for the worst-hit regions at somewhere between months and years. So now let's do the thing this channel exists to do. Let's actually run it, day by day. Hour 1. It starts beautifully. That's the cruel joke of it. The first sign is auroras. Green and red fire in the sky, visible from Texas, from Spain, from places that haven't seen them in a lifetime. People go outside, they point their phones up, then the streetlights flicker. And region by region, in minutes, the way Quebec went in 92 seconds, the grid folds. Day 1. Still feels like a normal blackout. Phones work. Cell towers have battery backup. People assume it's temporary because every blackout they've ever known was temporary. The misconception buys the disaster a full day of calm. But quietly, the clocks have started. Cell tower batteries, hours. Hospital generator fuel, days. The food in your fridge, 2 days. And the one nobody thinks about, water. City water pressure comes from electric pumps. In high-rises, taps are already sputtering. Day 3. The gas stations are the first hard wall. The tanks under the stations still have fuel, but the pumps that lift it are electric. No power, no gas, which means delivery trucks stop, which means the supermarkets, which run on just-in-time delivery and hold about 3 days of food, start showing empty shelves. Cash machines are down, card readers are down. Banking is a cloud service now, and the cloud has no power. Whatever paper cash was in your pocket when the storm hit, that's the money you have. Week 1. Water treatment plants exhaust their backup fuel. In the affected regions, tap water is now unsafe or simply absent. Hospitals are triaging fuel for generators and refrigerated medicine. Insulin, vaccines, is dying in warm storage rooms. And here's the mundane detail where the dread really lives. Sewage. Sewage systems need electric pumps too. 1 week in, the great achievement of modern civilization, the invisible removal of our own waste, quietly reverses. Month 1 and beyond. This is where the two futures split. Regions at the edge of the storm's footprint with intact transformers come back online. Weeks of chaos, an economic bruise, a global scare. But the regions that lost their transformers, they're waiting in a line hundreds of machines long, at factories on the other side of the world, each build measured in months. Lloyd's of London estimated the cost for the United States alone at up to $2.6 trillion and put full recovery for the worst-hit zones at up to a decade. Not the Stone Age. Nobody's wearing leather armor. It's stranger than that. A fully modern country where some regions function normally and others are effectively switched off for a year or more, waiting for a custom-built machine to arrive by rail. Okay, breathe. Because there are 2 genuinely good pieces of news and 1 asterisk. Good news 1. Unlike an earthquake, we can see this coming. A CME takes 1 to 3 days to travel from the sun to Earth. We have satellites watching the sun constantly. We would know something big was inbound. Good news 2. The grid isn't helpless. Warned in time, operators can do something that sounds insane but works. Deliberately shut the grid down. Power down the transformers, disconnect the lines, and let the storm pass over dead hardware. You'd trade a controlled blackout of hours or days for avoiding the blackout of months. Since 1989, utilities have gotten meaningfully better at this playbook. Now the asterisk. The one thing that determines whether a CME is catastrophic or a light show is the orientation of its magnetic field, and we can't measure that from far away. We only get that reading when the cloud crosses a satellite parked about 1 million miles out. At CME speeds, that gives the people who have to make the shut-it-all-down call a warning of somewhere between 15 minutes and 1 hour. 15 minutes to an hour. To decide whether to deliberately black out a continent, knowing that if you're wrong, you cause the blackout, and if you hesitate, you lose the grid for a year. That's not a technology problem. That's a 15-minute phone call where somebody has to be brave. So let's come back to July 2012 and that cloud crossing our orbit 9 days behind us. After it happened, a physicist named Pete Riley ran the numbers on storms like it. His estimate for the odds of a Carrington-class storm hitting Earth, roughly 12% per decade, 12% per decade. Roll those dice a few decades in a row, the rest of your life, say, and this stops looking like a freak event and starts looking like a scheduled one. The sun doesn't know we built any of this. It's been throwing these punches for 4.5 billion years. Every single one missed things that mattered, because there was nothing to hit. For the entire history of the Earth, a Carrington event was just a pretty light in the sky. Then, in about one human lifetime, we wrapped the planet in wire. The sun hasn't changed. We changed. We built a civilization that a 160-year-old event could switch off, and then we mostly forgot that event ever happened. In 1859, the storm found a telegraph. Next time, it finds everything. The only question left is the one we started with, 9 days. Next time, how many?